Okay, my friends, now we go to some terminology that we need. The first thing is what we mean by a subgraph or given graph. We mean that we take some vertices, some edges, and that we take the restriction of the incidence function to that set of edges, and if this structure is a graph, meaning that you have for each edge you have that its ends are in the set of vertices that we have taken, then you have what is called a subgraph. Among the subgraphs of a graph G, there is the graph G itself. If you have the subgraph which is not G itself, then you call it a proper subgraph. Okay? And a supergraph, where if H is a subgraph of G, then you say that G is a supergraph of H. What is a spanning subgraph? We'll be very much interested in some particular spanning subgraphs. A spanning subgraph is a subgraph which has the same vertices as G itself. And so, unless if it is a proper subgraph, it has some edges less than the original graph. Okay? When you have a graph which is not simple, you can delete all loops, you can delete all multiple edges but one between two vertices, and then you are left with a simple graph, okay? And that is called the underlying simple graph of G. In this case, you have here an example. You have a graph which has loops, which has multiple edges. You delete the loop, you delete all multiple edges but one. In this case, you delete one and leave one. You delete two here and leave one, and then these thick lines represent what is called the underlying simple graph of the given graph. Of course, if the graph is already a simple graph, its underlying simple graph is the graph itself. Okay? Then we have that. Okay, let's see a spanning. This is a spanning subgraph. Why? This is the graph, the original graph. The vertices are the same, and we have some missing edges. Okay, this is a proper spanning subgraph. Okay, and then we have various ways of determining the subgraph. For instance, we can take a certain non-empty subset of V, and we say that we can think of what is called the induced subgraph induced by V prime. What does it mean? Take the vertices of V prime, of course, and take all edges of the original graph with both ends in V prime. Okay, so if there was one edge with only one end in V prime and the other not, you don't take that edge because you don't have all vertices for it. Okay, in this case, you have here an example. Okay, for instance, you can take the induced graph. You take vertices U, V, and X. Okay, here you have U, V, and X. Okay, so you have what? You have an edge connecting U and V, no edges connecting U and X, V and X, and so what you get is this graph. It is one graph, okay? It is not two graphs. This is a graph. We'll have an adjective for describing this: disconnected, okay? it is done, it is built of two pieces, okay, we'll have a formal way of talking about that, but it is just one graph, okay? It is one graph, this with x, which will be called an isolated vertex, and this only edge between vertices u and b. Why? Because, for instance, edge b, it has an end which is v, but the other end is not in our set, and so you cannot take b inside. All right? Same thing if you let's see what's the next. You can also stress what the vertices you take out. If you are interested in that, you can say, I want to take out these vertices. This means the graph, the subgraph induced by the complement. So, for instance, if I want to take away, from graph G, I want to take away edges U and W, this means I keep all the other vertices and the edges between them, okay? So this is G minus U and W. U is this, W is this. This means the subgraph induced by X, Y, and V, okay? So I take both edges connecting Y with V, I keep the edge connecting Y with X, and no other edges, okay? I can do the same thing also for edges. So I can take a non-empty subset E prime of E, and I can take all the edges which are in E prime with their vertices. If a vertex is not an end of an edge in E prime, you don't take it, you don't keep it, okay? All right, and so you have this edge-induced subgraph. The same thing, you can say, I want to delete these edges. It means take the other edges and keep those remaining edges with their vertices. And so you have here examples of this by taking the edge-induced subgraph induced by edges A, C, E, and G. Okay? A, C, what are they? A, C, E, and G. So you have A, C, E, and G. This means you keep these four edges and all of their vertices, okay? And so actually you keep all the vertices in this case, but only these edges. Yes. All right, this is just terminology and notation, but we might be interested on using it. Okay, we often have to take away just one edge or add just one edge, and so we should put these brackets around the name of the edge. We avoid this in order to write a bit simpler things, okay? Two subgraphs of the graph G are disjoint if they don't have, if they have no vertex in common. Edge disjoint if they have no edge in common, okay? The union of two subgraphs, you have a big graph G, inside you have two subgraphs G1 and G2. B union is the subgraph in which you take the union of the two vertex sets of the two subgraphs and the union of the two edge sets of the two subgraphs, okay? The intersection is, you must have at least a vertex in common, and you take the intersection of two vertex sets and the intersection of the two edge sets. And you must have at least one vertex in common in order to be able to talk about the intersection of two subgraphs. So, this is the easy thing. This is the difficult thing. Find a bipartite graph that is not isomorphic to a subgraph over KQ. That's a really difficult problem in my opinion. Difficult to find a solution and more difficult to explain why that is a solution. Okay? So, what's the idea? Every K graph, every KQ is bipartite. We have already seen more than one explanation of that. And I got a very interesting one by a telecommunication person. Okay. Is there more here? Okay. All right. So we know that it's bipartite. Is it possible to have a non-bipartite graph as a subset of a bipartite one? Yes, indeed. And what you are asked for is to find a graph such that whatever K you take, there is no KQ containing that graph that you should exhibit as a subgraph of it. Okay? That's not easy. Try it. Not only, first, find one. There are probably several. I have one in mind. Find one, and that's already something. Second, explain why, prove that there cannot be any K2 containing it as a subgraph. Okay? All right. Now let's go to vertex degrees finally. The degree of V, of the vertex V in G, is the number of edges incident with V, each loop counting as two edges. Okay, that's why in the adjacency matrix we don't have the sum on each column as the degree, because there a loop counts as one, whereas for the degree you count it as two. Okay, if it is a simple graph, if it has no loops, actually the columns of the adjacency matrix give as a sum the degree of that vertex, but not if you have loops, because there is a difference of one. Okay? So, alright. Now we'll have very often these two symbols, small delta of G and capital delta of G, which are the minimum and maximum degrees of vertices present in G. Okay? We'll all very often use these two symbols. Small delta, capital delta, minimum, maximum degree of vertices present in the graph. Okay? Now we have already an interesting small theorem. There are various ways of proving that. One goes through the incidence matrix. So the idea is the sum of all degrees is equal to twice the number of edges. Okay? And let's see the proof that the authors give. Consider the incidence matrix. Okay, if you sum the entries in the row corresponding to vertex V, that is precisely the degree. Why? Because if you meet a loop, there you have two. Okay, and so you have a 1 for each link incident to that vertex corresponding to that row. Okay, and a 2 if you have a loop on that vertex. All right. So actually, the sum along a row is the degree of that particular vertex corresponding to that row. Okay? So if you sum all the entries of the matrix, it is like summing the sum along row 1 plus the sum along row 2 plus the sum along row mean, if you sum everything. Okay? And this gives you the sum of all degrees. Now you get the same sum of all the entries of the matrix if you first sum along column 1. How much do you have? One of the previous exercises, 2. Sum along the column 2 again, and so on and so forth. So you get that the same sum, seen as sum of the column sums, is what? Twice is 2 for each edge, and so it is actually 2 times epsilon. But the two sums are the same sum, the sum of all entries in the incidence matrix. Okay? All right. So that's a nice proof going through the incidence matrix. But I have also I like another possible proof. I count I count the edges when I am in a vertex. I count the edges incident to this vertex. Okay. And I count twice for a loop because I see 2 ends coming. Okay. So I count one for each link having me as an end, and I count twice for each loop. Okay, all right. So I have the degree of this vertex. I go to another vertex and I count, and I have the degree, and I have the degree. At the end, all edges have been counted twice. Okay, the loops because they are counted twice at the vertex where they are, and the links because they have been counted on one end and they have been counted on the other end. Okay, and so the sum of all degrees is actually the number of edges, but counted twice, so the number of edges times 2. Okay. 2 ways of saying the same thing, but the simplest one is surely the incidence matrix. Okay. Any problems about this proof? No. Very good. We can find a consequence of this corollary 1.1. In any graph, the number of vertices of odd degree is even. Okay, you will not be able to build a graph in which you have a vertex of degree 3, another vertex of degree 3, a vertex of degree 5, and all the other vertices at even degree. It's prohibited by logic, by this theorem. Let's see why. Split the set of vertices into 2 subsets. V1, the set of vertices of odd degree, and V2, the set of vertices of even degree. Okay? So what happens is that if you sum the degrees in V1, sum the degrees in V2, you sum the 2 sums, you get, of course, the sum of all degrees. Are you with me? Okay. But this sum of all degrees is an even number. Now, what about this number here? This is the sum of all even degrees in the graph. And so, is it even, odd, or what? Even. If you sum even numbers, you get an even number. Okay? Now, what happens here? Every addend in this sum is odd. Okay? And so, how will it be? I don't know. But if I take this number and sum it to this number, which is even, I get an even number. So this sum, is it even or odd? Even. But it is an even number which I get out of the sum of odd numbers. So, how many are these odd numbers? Even necessarily, because if I take odd plus odd, I get even. Odd plus odd, I get odd. Plus odd, even. Plus odd. Okay? So, the number of elements in this sum must be even, because this must be an even sum. Okay? And then you get this thing. You don't know anything about that graph. Which graph? Any graph. Take any possible graph and you find this thing. You cannot build a graph in which you have an odd number of vertices with odd degree. That's impossible. Okay? We were talking with the lady about possibility or impossibility of drawing some graph. Okay, we are already seeing something which is possible, something which is impossible for any conceivable graph, finite graphs, always finite. Okay? Any problems about that? Okay. Important. A k-regular graph is a graph in which every vertex has degree k. And so when you say a regular graph, it means it is k-regular for some k. If I'm not interested in knowing which is this number, I can say, take it a regular graph. How much a regular? 10, 2 regular, 3 regular, and so on. Okay. Okay. Now let's see some of these exercises. First of all, this. If you take small delta, then you have this inequality. Small delta less than or equal to 2 times epsilon divided by me, less than or equal to capital delta. How could we prove that? Small delta is the minimum degree of these vertices. Capital delta is the maximum degree of the vertices of that graph. How can we prove that? Any idea? Do you want a hint? The hint is multiply everything by me. Epsilon. Okay, multiply by me and try to prove this. It's completely equivalent, isn't it? If you prove this, you also prove this, okay? Is that maybe easier? This is one of the things that we don't have in analysis, but we do have in discrete and even finite mathematics like this. What can I do? I can visit every vertex and look at the degree there. So I start degree of V1. What can I say about the degree of V1? Of course, it is greater than or equal to this and less than or equal to this by the definition of small and capital deltas. Let's do it for V2. Now you sum everything. What do you get here? There are ni vertices, so near ni inequalities. So here you get ni times small delta. And here, ni times capital delta. And here, what do you get? You get the sum of, for I equal 1 up to ni, of the degree of the I. But what do you know about this? You know that this is twice epsilon by the previous proposition. And so you get exactly that all the inequalities are kept, and so you get this equality, you divide by me, this is me, you divide by me and you get this one, okay? Again, I wanted to show you this, not because it is particularly important, but because it is an example of what you can do by thinking in a totally abstract way, but at something which is finite. So, okay, I can do this sum. I don't have limits or things like that. Okay. Oh, I like this very much. Show that in the group, in any group of 2 or more people, there are always, always 2 with exactly the same number of friends inside the group. Meaning, take one username, one Facebook username for each of you, okay? So I take all of you, all right? And I build the graph of friendships among you. There might be someone who doesn't have a friend here, okay? Counts, it has degree 0 in this graph, okay? And what they say here is that there are always at least, it should be written like this, at least 2 with exactly the same number of friends inside the group. Meaning there are at least 2 vertices with the same degree. How can you prove that? Which might be 0, for instance. It is similar to this. I like that other. Take the students of engineering of Bologna. Okay, they are roughly 9,000, 10,000. All right. In this moment, who are in this moment students of engineering in Bologna. Okay? Can you prove that there are at least 2 who celebrate birthday in the same day of the year? Another one. Oh, I need to see people like him, you, also you. Yeah. There are people with a lot of hair on the body, okay? Or also you, okay. All right. But even me, even you don't have a million hair. All together, you don't have. Let's take the maximum you have a million. Take away all bald people in the world. In this moment, there are at least 2 persons in the world with the same number of hairs in the world. I needed to fix the moment because hairs are falling all the time. Isn't it true, guys? Not yet. Wait a minute and you'll see how they fall at each moment. Okay? How can we prove these 3 things? That one, similarly, there are at least 2 persons in the engineering faculty celebrating birthday the same day, and there were at that moment 2 persons, at least 2 persons with exactly the same number of hairs in their bodies.
Like there should be people that have the same number of birthday because they want to see how to days, but infinite numbers of hairs, how many?
No, not a
There are not.
not even a million, maybe 200,000.
But there is a fixed number.
There is a finite number which is rather small in comparison with the number of people. But let's formalize things in a mathematical way. Let's take the people in engineering. You take this set X, the set of people in the engineering faculty, and you take the base in a year, okay? And if you make a function sending each person to his or her birthday. Can it be injective, meaning what is injective? That two different objects in the domain go to two different objects in the range. Not if you have that the domain has more objects than the range. And this is the case. I cannot be sure that there is somebody who celebrates on the 15th of April. That I don't know. It might also be that nobody in the engineering faculty celebrates on the 15th of April. But I'm totally sure that you cannot have a different birthday for each one. Why? Because there are 9,000 people going to 365 or 366 different dates. Also, take the people on the world. To each person, give the number of hairs in that moment, okay? So you have 7 billion people. Let's take away 1 billion of bald people, I think I exaggerated. So 6 billion people, and you have only, let's say, 1 million possible numbers of hairs. And so you cannot have an injective application from that to that. Now, let's take a graph, a simple graph, because being friends is a simple graph, okay? You cannot be friendship with yourself. I'm taking usernames, single usernames, okay? Now, then, what do you have? You have, say, 15 vertices in your graph. How many possible degrees are there? Okay, if there are people with 0, if there is just one person with 0, take it away and consider the others. Okay, if there are 2 people with 0, okay, you are already done. There are 2 people with exactly the same number, 0 of friends inside this community. But take people with 0 friends away. So you don't have any the possibility of degree 0. So you have, if you take 15 people, none of them with 0, you have possibilities of degree 1, 2, up to 14. So the possible degrees are 14, but you have 15 vertices, and so if you associate to each vertex its degree, this application cannot be injective because you have 15 in the domain and 14 in the range. And so necessarily in a graph with no isolated vertices, there are at least 2 vertices with the same degree, which is what is said inside that exercise. Okay? See you next month.